Welcome, everyone. Thank you for joining this new distinguished lecture offered by the IEEE AESS. We will give a brief introduction on the AESS, followed by an introduction of the speaker, Dr. Eli Brookner. The AESS is a relatively small technical society, but thriving in terms of its activities and offering to its members. My name is Lorenzo Lomonte, and I am the Vice President for Education, and I'm speaking here on behalf of the President of AESS, Mr. Walt Downing. Now, it's time to present the speaker of today, distinguished lecture, Dr. Eli Brookner. Dr. Eli Brookner has been working for more than 50 years at Raytheon, and he won many awards. Here I'm just listing a few of them: the IEEE Picard Medal Award in Radar, the IEEE AESS World and Wide Award. Dr. Brookner also wrote more than at least 4 books that I'm aware of, and he also wrote a cover story on Scientific American on phase array, which actually had more than 600,000 copies in circulation, and many other achievements. Today's lecture will be entitled Radar, Phase Array, Metamaterials, Invisible Man, Stealth, Ultra-Wideband, Cognitive Adaptivity, MIMO, 5G, Advances and Breakthrough. So it's really a lecture about the current and the future of radar system. And before beginning the lecture, I just want to point out one rule. If you have any question, please leave it under question and answer tab of Zoom, not in the chat room. And I believe that now it's time to give control to the speaker, Dr. Eli Brookner.
Hello, everybody. The title of the talk, as indicated, it's IEEE AES Virtual Distinguished Lecture. My contact information here, what I look like. This is a very important view graph here. On the left is you before the talk, haggard and unhappy. And on the right is you after the talk, fat with knowledge and a little humor. I like to give a little bit of history. What did we do in World War I with respect to radar? We did have radar in World War I. Acoustic radar, passive acoustic radar, listening to the engines from airplanes. 2 receivers gives us angle information, monopulse. An array gives us ASL. What did we do in World War II? In my travels, I came across a fan beam radar, very modern fan beam radar in South Korea. Here it is. Since World War II, phased arrays have seen amazing advances. An example is the Cobra-Dane radar, not your ordinary radar. Here it is, a picture of it I took. 95 feet in diameter. Here's me standing in front of the array looking up. It has 35,000 radiating elements. Those are the circular discs shown on the slide here. 35,000. Very impressive. Main purpose of the radar is to monitor the test firing of the Russian missiles to ensure that they abide by the SALT I negotiations with respect to the size of the re-entry vehicles per booster and the number of re-entry vehicles. The antenna, as I said, is 95 feet in diameter. It's broken up into smaller antennas called subarrays. There are 96 of these subarrays. Each one is fed by a high-power traveling wave tube with 1.6 megawatts peak power and 10 kilowatts average. Here we are on the ground floor of the radar. we see the 42,000 volt power supplies which service those TWTs. On the next floor is the modulator banks. There are 12 of these, each one serviced by one of those 42,000 volt power supplies. On the top here are the bottoms of the TWTs. For each modulator bank, there are 8 TWTs serviced. The outputs of those TWTs are shown here in 3-inch flex coax. Here's one of the coaxes going to one of the small antennas feeding the small subarray antenna, consisting of 160 radiating elements, each one fed by a 5-bit phase shifter. Here we are looking through the center of the array, and we see 10 subarrays, a lot of hardware. This is called the first generation of phased arrays, consists of tube transmitters, tubes. And here's a US tube transmitter phased arrays, first generation. Here's from other countries. The second generation phased arrays use transistors for the power amplifiers. No tubes. An example is the pause radar, another big radar. This one has 2 radars in one site. There's 2 faces here. And it's bigger in diameter. It has a diameter of 102 feet each face. The frequency of this radar is UHF, roughly 400 megahertz. The Cobra Dane is a higher frequency of about 1200 megahertz. Here's one of the transistors used for the power amplifiers. It's 115 watts peak, consisting of the paralleling of many transistors with bonded wires. We call this phased array an active electronically scanned array, or AESA. It's called active because it has a power amplifier at every element, in contrast to the tube ones, which had one tube feeding many elements and only passive phase shifters at the elements. Here we are inside the array, looking through the center of the array, and it looks empty, like it's not finished. All we see is the 28 volt power supplies here, and you can't see the transmit receiver hardware. They're plugged right into the back of the array on the right. This is in contrast to the tube array, that Cobra Dane, where we see all this hardware in the same place in the array. You see the big advantage here of a tube array, of a solid state array. Here I am standing in front of the array, the pause array. It consists of dipole radiating elements, bent dipole radiating elements. That picture served as the cover of the Scientific American paper that was mentioned, which was an article on how phased array radars work. I recommend the paper very strongly. It's a very good paper. I can get you a copy. As I indicated, the radiating elements are bent dipoles, and the reason for the bending of the dipoles is to reduce the mutual coupling between the elements. If you have too high a mutual coupling between the elements, it turns out you can have all the power from the transmitter reflected back into the radar, none of it going out. They call that a blind spot when you have that situation, because you don't radiate, so you can't see the targets. Worse than that, if it's a high power radar, all the power going back into the radar would heat it up and cause a fire, as shown here. This is the first large phased array built in the US burning down. I was told the reason for this is that they had the power going back into the radar because of the blindness, and this created the fire. It turns out that's not true. The only reason for the fire was a simple short. Here's some example of the second generation transistor phased arrays. The third generation of phased arrays used analog microwave integrated circuits, or what's called MMIC, monolithic microwave integrated circuits, for the AESAs and for the solid state transmitters. Got rid of the bonded wires. And here are examples of some for land and sea application, third generation, airborne, fighter aircraft, space. The two on the left are satellite systems for telephone communications. The far left one is the Iridium, which had worldwide communication for telephone from the ground to the satellites to another person on the ground anywhere in the world. I could have used that system when I was in Papua New Guinea in 1992. It's a small island north of Australia, had very poor roads and very poor telephone system. I could have used that Iridium system. Here's one of the natives. You see that thing through his nose? You know what that is? That's a dipole antenna. That's their Iridium system. They have to operate in the New Guinea wet jungle, which required penetrating through the wet jungle to the satellite systems. And the Iridium system would have a hard time doing that. So they use a lower frequency and therefore a very long dipole radiating element. Very advanced technology. Here's the Patriot system. That's actually a first generation radar, which has been upgraded to be a state-of-the-art third generation phased array. Who said you can't upgrade an old radar? This is an example of one case where it was done. The Army plans to use this radar all the way out to 2048 because of that upgrade. Replace the tube radar with a transistor integrated circuit third generation antenna and all the tubes in the rear receiver by transistors. The FAA, Federal Aviation Agency in the US, is planning to replace all the air traffic control radars in the US, which are rotating antennas with third generation phased arrays. It would be 350 AESA radars, a program costing about $4 billion. It would be four-phase phased arrays or cylindrical arrays. Lincoln Lab MIT has built a demo for the four-phase phased array using low-cost commercial off-the-shelf hardware at S-band. They use printed circuit boards for the antenna and patch radiating elements, low cost, for the radiating elements. And for the TR modules, they have plastic chips, no expensive hermetically sealed vacuum packed TR modules. You can also get 360-degree coverage using a dome antenna. And here's a dome antenna, and I'm shorting it. And on the right and the left, you see the grading lobes of the dome antenna. Now, the fourth generation phased arrays use digital beamforming. If you had no digital beamforming or analog beamforming, to form two beams, you need two sets of phase shifters and two combiners. If you wanted 10 beams, you needed 10 phase shifters and 10 combiners. With digital beamforming, all you need is an A to the D at every element, and then a computer to calculate the beams. And depending on your capability of your computer, you can generate as many beams as it's capable of, 10 beams, and if technology improves, you can replace it to form 20 beams. So a very nice technology, and the wave of the future using such technology is where it's going. Here's examples of some for ground and sea. This one is for sea. It's the AMDR, Air and Missile Defense Radar. It's to replace the venerable Aegis radar that's been placed on over 80 ships. This radar, the replacement, will have 30 times the sensitivity of the older Aegis radar and capable of tracking 30 times as many targets. The advantage of digital beamforming is it allows you to have multiple independent beams. In my travels, I've seen such radars with independent beams. Here's one, a 3-beam system in Borneo, a multiple beam system with different size beams in Borneo. With digital beamforming, you could correct for missing elements and for bad elements. Second advantage of digital beamforming is that it requires, for doing volume search, half the power that a non-digital beamforming radar would require. And it does the search in half the time and provides the location of the detected target to higher accuracy than the non-digital beamforming. A third advantage of digital beamforming, it enables cognitive adaptive array processing, what I call CAP. Some references for it. What's it all about? Make use of all the information available. And if it's not available, find it if it's easy to find, and makes your life easier. An example here, consider a linear array of n elements. The first thing you do is, with digital beamforming, search the sky, the field of view, to see where the jammers are. Let's assume there's only one jammer. On the bottom here, I have the focused beams that are formed digitally that cover the whole field of view. If there's one jammer, you'll find one of the outputs having a larger noise output. That would be the one with the jammer. With the cognitive approach of cancellation, you take the output of that channel, which I call the auxiliary beam or jammer beam, and use the signal from that beam, the jammer signal from that beam, to cancel out the jammer in a beam that's looking for a target at another location. Let's assume it's at boresight, looking at boresight as shown here, with side lobes that are 40 dB down. I'm going to assume, so the beam is pointing on boresight here, 0 angle, and I'm going to assume there's a jammer in the second side lobe to the right of the main lobe, and we want to get rid of it. We get rid of it as I described, and when we do the cancellation of the jammer, the antenna pattern in the main beam looks as shown here. The side lobes are still at 40 dB down, except for 2 straddling the jammer, which is at where there's a null in the antenna pattern, as there should be, to cancel out the jammer. And those two side lobes are only degraded by 2 dB. Now, this is in contrast to when we use the classical technique for canceling out a jammer for a phased array, the sample matrix inversion method. When you use that method for this example, here's what you get for the adapted beam. You do get a null where the jammer is at 20 degrees, and the main beam is pointing at bore site. But all the other side lobes are degraded by 20 to 30 dB, whereas before, only 2 were degraded by only 2 dB. And here we used more training samples, 32, to achieve this, whereas for the cognitive approach, we only had 4 training samples. Things would be even worse for the classical approach if we had more than 16 elements that we assumed in the preceding example. Let's assume 10,000 elements in the array. In that case, for the classical approach, you need 50,000 training samples. In contrast, for the 10,000 array element with the cognitive approach, you only need 4 training samples still. The number of training samples is only 4, independent of the size of the array, a big advantage of the cognitive approach. In addition, for the classical approach, one needs to invert a matrix that's 10,000 by 10,000 in size when you have a 10,000 element array. And to do that requires about 1 trillion complex multiplies and divides. In contrast, the cognitive approach only requires 5 complex multiplies and divides, a huge difference. In the future, ultimately, the digital beamforming will consist of an A to D and D to A at every element to get take best advantage of the digital beamforming. When doing this, one has the advantage that for a given antenna, and I have the antenna array here, you can use part of the antenna for different parts of the antenna for different purposes, like part for radar, comm, and EW on the left here. And later, if you needed more capability with comm, you would use a larger part for comm and less of the aperture for radar. And you can do this in microseconds. That's an advantage you'd have if you had an A to D and D to A at every element. People are building radars which have an A to D at every element now on receive. One example is from Elter in Israel, a 4-phase phased array for shipboard application at S-band with 2,500 elements per aperture, a A to D at every element. Australia has one, which is a 6-phase phased array, 6-phased phased array at S-band, digital beamforming at every element. That's the company CEA at Australia. Thales has one from their Dutch division, having 1,000 elements at S-band with an A to D at every element. Here I have Lockheed Martin's contribution, a very impressive one. It's for the Space Fence program to track satellites and space debris to be deployed in Kwajalein, the first one, which has an A to D at every receive element. And the receiver has 86,000 receive elements. Dual polarized, so it has 172,000 receive channels with an A to D at every channel. Very impressive. You have to give them credit for this system. Not to be outdone, Raytheon developed an A to D that is reconfigurable. It allows your phased array to be used at S-band or X-band on demand, switchable in microseconds, with an instantaneous bandwidth of over 400 megahertz. Xilinx has commercially available chips that allow you to build a digital beamforming array for transmit and receive. That's a D to A for transmit and an A to D for receive. A very impressive one at X-band with a bandwidth of about 1 gigahertz. The A to D has 12 bits, 4 gigasamples per second, and the D to A's have 14 bits, 6 gigasamples per second. And the array shown on this figure is about a foot by a foot, made of the chips, gate array chips, commercially available. Very impressive. I like to show some of my travel slides in China at the tea house sitting there, Tiananmen Square, opera singer. A holy man in Nepal at a cremation site. A tribe woman in Thailand. I had to walk 20 miles through the rainforest to see her. Very, very impressive here. And at a radar conference, the banquet at an IEEE radar conference held in Kyoto, Japan. I recommend you go to our radar conferences. They are very culturally enjoyable. Here's a woman studying to be a beautician in Russia. There's a woman in Sweden who stopped me for directions. I couldn't help her, but I got her picture. And that's me. What makes digital beamforming feasible is Moore's law. That's the doubling of the number of transistors per unit area every 2 years. People say that Moore's law has stopped. It hasn't stopped. It's just slowed down, but it's still moving along very impressively. When I started working on electronics in high school, I used tubes. There were no transistors back then. These are 1 inch by 2 inch tubes, glass tubes. I built a radio and an oscilloscope. Now I carry in my back pocket a memory stick. Has 256 gigabytes of memory. Consists of 260 billion transistors. That's equivalent to using 260 billion tubes, the tubes I used, 1 inch by 2 inches, twice the size of one of these sticks. At $1 a tube, if I use tubes to do what this stick does, it would cost $260 billion, $1 a tube. And with 1 watt per tube for the filaments, it would require 260 gigawatts, which is 260 nuclear power plants. Furthermore, if you stack these tubes one on top of the other, they would go to a height 18 times the distance to the moon. Very impressive what's happened during my career. Incredible, incredible. Another thing that is incredible is the wiring on such chips. In a chip that's 1 centimeter by 1 centimeter in size, there is 10 kilometers or 6 miles of copper wiring. 6 miles of copper wiring on a 1 centimeter by 1 centimeter chip. Incredible. That what I just described is the integration for digital circuits. What about for microwave circuits? We've come a long way there also, not quite as far, but we can now put all the transmit and receive circuitry we need for a phased array consisting of 32 elements at 60 gigahertz on one chip. One chip. This is an Intel chip shown here. And in more advanced is the ability to do it for a 256 element array at 60 gigahertz to put it on one chip. It's about a 1 1/4 inch chip. Work done by Dr. Rebez at the University of San Diego, California. I call this extreme mimic. Future phased arrays will cost, according to Rebez, $1 per element. Very low cost. Could be used in the future in your cell phones, going up to satellites or cell towers for 5G. Here I show a small chip on a fingertip. That chip has all the microwave and RF circuitry you need for a 77 gigahertz radar. Very impressive. Future radars like that would only cost a few dollars. Google has put a radar on a wristwatch. They actually have it in their latest cell phones. It is a radar for controlling the screen by your finger motions, like sign language. Having that wristwatch radar reminds me of my childhood days when I read Dick Tracy. He had a cell phone wristwatch. We're catching up to Dick Tracy. The human brain only weighs 2 to 3 pounds and only requires about 20 watts. A mouse's brain is less capable than a human brain. And if you were to build a computer with today's technology to do what a mouse's brain does, it would be the size of a small city and require several nuclear power plants to run it. So when it comes to doing what our brain does, we are in the horse and buggy days. We have a long way to go. And what's out there that's going to make it possible? Well, quantum computing is one technology. Synaptic transistors, work done by Harvard University. The use of graphene transistors. These transistors have a clock speed of 1,000 gigahertz, 1 terahertz, about 300 times what we have in our laptops. On the left here is the man who got the Nobel Prize for his work on graphene. I'm rubbing shoulders with him. I figured it'd rub off. It didn't. It is believed that with the memristor, that's one of the electric circuit components, the fourth one, the first three being capacitor, inductor, and resistor, that with a memristor, you can do what a mouse's brain does in a shoebox-sized computer. That not being funded yet, though. In the meantime, Everybody should buy their own radar. It's now affordable. If you go on eBay, at least they used to have, for $20, a speed gun radar similar to what the policemen have. $20. Now, I used to work at Raytheon, and one of its employees beat Einstein. When you beat Einstein, you have to brag about it. Here's the cover of the Microwave Journal. It's a journal we engineers get, has a circulation of about 45,000 issues every month. And one of the issues they had on the cover, over 100 famous living and past scientists like Marconi, Maxwell, Armstrong, Faraday, Hertz, Leonardo da Vinci, Newton, Einstein, of course. And if you look at the lower left-hand corner, who's that in the lower left-hand corner? That's me. I'm with all these famous people. And if you look under the C here, up here, you find me again. I appear on the cover twice. Einstein only appeared once. I beat Einstein and all those other famous scientists. I also appeared on the cover of the AESS magazine, dancing. Einstein never appeared on the cover dancing. And here I am dancing with Sarah Palin on Dancing with the Stars. What's going to make electronics low cost in the future is printed electronics. We're able now to print a diode circuit operating at 1.6 gigahertz, and that frequency will go up. In the far term, it's predicted that if you live to the year 2045, you will reach immortality, because by that time, we will figure out how to cure all diseases and maintain your health. What will be the fifth generation of phased arrays? One possibility is ultra-wideband AESAs. A lot of work going on in that area, especially for airborne radars. And another possibility is radars on a chip, antennas on a chip. Here's a wideband antenna, a conformal one that can go from like 1 gigahertz all the way up to 20 gigahertz. And its thickness for the lowest frequency is lambda over 40. It's called a tightly coupled dipole array. Could be used for wideband radar and also for escort jammers, as shown here. New subject, metamaterials. What is metamaterials? It's materials on demand. We are not satisfied with what nature provides. We want more. We want properties we can't find in nature. And with metamaterials, we can create such materials that have properties not found. One way to do this is have little structures smaller than a wavelength we want to apply the material to, and put it in an array in a substrate. That'll give you characteristics you can't get in nature, like a negative, you can get an invisible man as a result. How does that work? Here on the left, I show a sphere. You surround it with the metamaterial, and the electromagnetic waves go around through the metamaterial to the other side without being blocked by the sphere. No reflection. So the sphere becomes invisible. They call this cloaking. And it has been demonstrated. First, let me show, if you had a array of wires, you get a negative epsilon. If you had an array of split rings, you get a negative mu. And you interleave the two, you get a negative index of refraction, which could give you invisible targets. It has been demonstrated at S-band. The hole here is 5 centimeters diameter. You put the object you want to hide in there, and around it, they have your metamaterial. The signal goes around the object, and the target becomes invisible. It works, except it's a very narrow band at S-band, and it requires a very thick cloak, about 6 centimeters in diameter and width. Not practical for many applications like airplanes. Another possibility is to use fractal metamaterials, what I call fractal metamaterials. It's fractals, which is a repeat of different size, in this case, rectangles. It's work carried out at a company in the Boston area called Fractal, owned by Nathan Cohen, the chief scientist and owner there. Using fractals, he was able to do cloaking at L-band with a 50% bandwidth. Very impressive. And the thickness of the cloak, I believe, was about a ½ inch. Another application for metamaterials in the future is low cost electronically scanned antennas for applications on airplanes, cars, railroad trains, in your suitcase at home. It would allow you to have, using satellites, worldwide high-speed internet. Here's the satellites. It would use these antennas also. That work is in progress right at the moment, and we wait to see how it develops. Another way to get low cross-section for your target is, instead of having it go around the target, cover it with material that absorbs the incident wave. And that has been demonstrated to work at a frequency of 8 to 10 gigahertz band, giving 6 dB of absorption, reduce the cross-section 6 dB with a flexible metamaterial sheet of split rings. The Chinese are working using fractals for achieving the same goal. Their fractal coating allows you to get 10 dB absorption over a very wide bandwidth from 2 to 20 gigahertz, and 20 dB absorption from 10 to 15 gigahertz. On top of that, it's very thin, less than a millimeter thick, and it works for all incidence angles and all polarizations. Very promising technology. Work being done by China, published in 2013. I did a search recently and found no follow-up. I imagine they put a clamp on it. And I would imagine similar work going on in the US and not being published. It's very promising technology. Now, metamaterials is not new. The Romans used it for their glassware to get colored pictures on their glassware using metamaterials. They would put blobs of silver or gold, small, through the molten glass to form the pictures at different colors. These are shown here. The same technology was used for the colored windows in the cathedrals in Europe Another new topic, MIMO. MIMO is one of the latest things in phased arrays. Stands for multiple input, multiple output. On the left, I have an array. For a conventional array, we radiate with the same waveform from all radiating elements at the same frequency, normally. With MIMO, you radiate with a different signal from each radiating element. These are noise-like signals typically, which are orthogonal to each other. The advantage of this is that in the receiver, when you get the echoes from these different elements, you can separate these signals and then put phase shifts on them in the receiver that you would put on them to form a focused beam on transmit if you use the conventional beamforming. So with MIMO, you form the transmit focus beam in the receiver. Let me say it again. You form your focus beam in the receiver instead of in the transmitter. Now, with a different beam signal for each element, you can't form a focus beam on transmit because the phases will be independent from element to element. And then as a result, the transmit beam pattern is that of a single element, like 120 degrees wide. It has an advantage. With one transmission, you cover your whole field of view of 120 degrees. And you form your focus beams in the receiver. And you can form them as many as you want and with different spacings. Here I show the architecture. It consists of, each element in the receiver has matched filters, which picks out one of the N transmit signals and rejects all the others. So you can isolate those signals and put in the phase shifts in the receiver that you would have put in for a conventional array on transmit to get a focus beam at a given angle, let's say theta sub k. And you can form as many of these beams as you want. And here I show the formation of such beams. The black curve is that of an element, and the red is that of the focus beams on receive, and also represents the focus beams on transmits. And you can form as many of these as your signal processor permits. This has a big advantage. By putting out more beams, by forming more beams, you reduce your beam shape loss, your receive beam shape loss, and also reduce similarly your transmit one. Very nice advantage for MIMO. This is a monostatic system. One architecture that's received a lot of attention for MIMO is where you have a different antenna for transmit and receive. For receive, you have an antenna of N elements, a linear array. Let's say N is 10 in this case, with lambda over 2 spacing, so it doesn't have any grading lobes. But on transmit, you have a thinned array, which has much wider spacing. For N equals 10, you have 10 times the spacing between elements. And as a result, you have 10 grading lobes. Now you transmit a different waveform from each element and you process it. And it turns out it was shown that when you do this, gets you the equivalent of an array of 100 elements, N squared, N being 10, with lambda over 2 spacing. So with a 20 element receive array and 10 element rather, 20 elements altogether, you get the performance of a 100-element array with lambda over 2 spacing, no grading lobes. A big advantage. If n were 1,000, you'd get 1,000 better resolution. It would be equivalent to a 1,000,000 element radiating elements, array of elements at lambda over 2 spacing, no grading lobes. A factor of 1,000 better resolution than a conventional array. The only trouble is, well, they claim that MIMO has orders of magnitude better resolution and accuracy than conventional arrays. Only trouble is it's not true. They didn't do due diligence for what conventional arrays could do. Using the same antennas they use for the MIMO, and if you use it properly, you can have a conventional array give you the same performance, the same accuracy and resolution as the MIMO array. So they're equivalent. They don't give you orders of magnitude better performance. In my travels, I came across MIMO systems. There's a multiple output, multiple input system. Here again, this is at a festival in Singapore, Hindu festival, where they dedicate a ceremony dedicating a mountain god. 600 men do this every year. This view graph compares MIMO with conventional arrays. For example, point out that MIMO is no better with coping against a barrage jammer or a hot clutter jammer than a conventional array. And as a matter of fact, for a repeater jammer, conventional can do better. And I'll leave you to read the rest at your leisure. Hot clutter is jammer signals coming to the receiver after bouncing off the ground. Now, a type of MIMO array that's received a lot of attention, it looks very promising, is for cars. It also consists of a full array of n elements, lambda over 2 spacing, no grading lobes, and a thinned array for transmit. Except now the thinned array only consists of 2 elements, again with n times the spacing of that of the full array. Using this combination, it's shown that it's equivalent to having having a conventional array of n 2n elements. So you get twice the better, factor of 2 better resolution and accuracy using MIMO with this automobile architecture or vehicle architecture. Again, they didn't do due diligence, and I believe you can show you get this equivalent accuracy with a conventional array. And I did it also for a case where I got only 15% better with MIMO than a conventional array. So not a factor of 2 better. Future applications of MIMO, well, for car radars and for OTH. For cars in Israel, they're using it for inside the car as well as outside the car. The idea is to use it for determining when's best to deploy the airbag during a crash to minimize injury to the passenger. It replaces a stereo camera that's much more expensive. Another application future for MIMO is, let's say you have a radar in production and the enemy has reduced its cross-section factor of 9 dB. You need 9 dB more sensitivity. What you could do is take 2 of the radars in production and use them in a MIMO mode. And when you do that, you get 9 dB better sensitivity. Lingen Lab does this regularly with ease in their demo at the lab and showed it to me. Suggested future work on MIMO is given here. I let you read that at your leisure. A new topic. What else is new in radar? There's the holographic radar. A radar from Thales. They bought a small company called Avalant, which doesn't require a rotating antenna, stationary antennas. How does it work? It transmits with a spoil beam, and on receive, it has a simultaneously and focus beams to cover the field of view as shown here. Merrill Skolnick calls this the ubiquitous radar. So they are making what's Merrill called the ubiquitous radar. And it's being used at various locations at airports and in windmill farms with success. So it's another tool in our toolbox of radars. Very nice. What else is new? Quantum radar. What's that all about? Well, there's the entanglement between particles. It's the fact that if you change the state of one particle, the particle it's entangled with will change almost instantaneously. It occurs at such a speed that even going at the speed of light, it requires much faster communication than the speed of light. Einstein called this spooky physics. It's indeed spooky, but they plan to use this to enhance the sensitivity of radars, to defeat stealth. One group in the West is working on it. A fellow from MIT involved, and another group from China. It's being funded, both places, and warranted, and we wait with excitement to see what happens. Here's some references on MIMO and breakthroughs in related topics. I recommend this conference on phased arrays. It's given in Boston, given every 3 years. We get the leaders in the field from research facilities, companies, and universities. The flags indicate the countries that have attended. This talk is given, obviously, as a distinguished lecture. Some of my books, I like red covers. And here's me going around the world fixing radars, a very sick radar here, and I'm telling it to take 2 transistors and call me in the morning. That's me again. We must be at the end. And hopefully you're on the right with knowledge and a little humor. We're open for questions. Thank you.
Thank you very much, Eli, for this very inspiring presentation. We do have a few questions here, and I'll read them for you. So one is from Larry Chastain, and the question is about, he wants your opinion on noise radar. He says noise radar was the topic of the September issue on the System magazine, and he wants to know your opinion on noise radar.
Yes. The thing is, typically we don't use a noise waveform for radars. The waveforms we use typically are chirp waveforms, or pulse Doppler waveforms. They work very well, very, very well. Noise waveforms are not a trivial waveform. They have a complicated structure as far as side lobes and require a lot of processing. So from a practical point of view, we find the chirp waveform, which is Doppler invariant and easy to process, a very good waveform, and we use it a lot. There have been systems that have used noise-like waveforms, but they haven't been that beneficial and haven't really caught on. So it's a thing that may in the future be used more, but right now the tendency is to go for the low cost, very well has good properties waveforms we use.
Okay. I have another question from Jack Ding, and he is asking just to provide a comment on quantum radar.
Oh, I believe it's worth funding to see how well it really works. It does require more work to see if it really will help in defeating stealth. And it warrants funding for that reason because it has a potential. And we'll see what happens. They are funding it. A number of people in the US and overseas in China. The US one includes Western world engineers as well and scientists. So we will, it's an exciting area and hopefully maybe something will come of it.
Very good. So I have another question here. It says, how does a phase array perform when the jammer is at the target? Can you get any benefit from phase array or digital beamforming to reduce the jammer, or should you use another signal processing approach? Let me read this one again. Probably.
Yeah, no, I think I hear what he's saying.
Yeah.
When the jammer's at the target, it's a very difficult problem. It's a tough problem when the jammer.
When the jammer is the target, sorry, when the jammer is the target.
Right, but he does have a disadvantage, though. You know, if you know that he's doing this, you know where the jammer, you know where the target is.
Mm-hmm. Yeah,
So
exactly. That's home on jam, I would say, right? Yeah.
Then you know, if you have two receivers, you'll know where he is in range and angle. So it does have its issues, and you know, it has its problems and it has its issues. It's not all one-sided.
Yeah.
It's very difficult to cancel a jammer like that because it's in the main lobe, and when you cancel the jammer, you'll be canceling the signal.
Yeah, but at the end, you will know that the jammer is there.
You'll know it's there, and if you have two receivers, you'll know exactly where he is.
Yeah. The other question is, what about impulse radar?
That's the same as wideband. Let me make a comment on that. There was work funded by DARPA, Defense Agency of the US, because somebody from Boeing claimed that with an impulse radar, they can defeat stealth targets. Short pulse radars would be defeated by impulse radars. Fourier transforms didn't work, they claimed. And there was a very high level study carried out with leaders in the field. And I thought it was overkill, but it turns out they needed that group because the people who made the claim were very difficult to deal with. They accused the committee of stealing his ideas and lying. And It was actually went to a group to evaluate whether there was a fair treatment of the topic. The bottom line is that impulse radar does not defeat self.
Very good. Then another question.
We had to pay $2 million to prove it. We actually measured it, the measurement. And I presented the data. I was very honored to present the data. Very good.
Can you explain why digital beamforming can gain half power and half time in search mode?
Very good, very good. The reason is when you have digital beamforming, it becomes feasible to have multiple beams on receive. When you have multiple beams on receive, then you reduce the receive beam shape loss. Because if you have a lot of beams, no matter where the target is, he's going to be near the peak of one of these receive beams, right? So there's no receive beam shape loss. He's always near the peak of a receive beam. So you remove the receive beam shape loss. And when you do that, if you have roughly a Gaussian shaped beam, it turns out that your spacing between the beams is a square root of 2 further apart to do the search, both in as and L. And that gives you a factor of 2.
Yeah.
It's very beautiful, that you get that factor of 2 by having digital beamforming be available to form multiple beams on receive to eliminate your receive beam shape loss. You do have your transmit beam shape loss.
Yeah.
It turns out with MIMO,
you
can also reduce
both of them. Yes.
Because you can do the beamforming in the transmit beamforming in your receiver.
Yep.
And you form beams at different angles. And that lowers that beam shape loss as well. So a nice feature of MIMO.
Another question
people say I'm always against MIMO, but I wanted to point out some nice advantage. A nice feature. Okay, I'm sorry.
No, another question. So how large a time bandwidth product can achieve given today's processing capabilities? I mean, I guess the question is how wide you can make a time bandwidth product in modern days computer?
I don't know. We never had a problem. We can always do whatever we needed. There is a limit, but that would be because the limits of nature, right? Mm-hmm. There's only so much time you can wait for your echo because you want to send out another signal. That's there's no issue there. Let me say it that way. It's not an issue. You're limited by practicalities.
Yeah.
Where the limits of the world.
You're right. Another question from Martin. Could you please comment on the use of phase arrays on passive radar application?
Oh, passive. That's getting a lot of attention because it's low cost. You make use of somebody else's transmitter, right? And it's a nice feature. As a matter of fact, if you wanted to build a radar, that would be the way to do it. You'd fortunately like to have your radar be located near airports where there's a radar or one of the radars across the country, and take advantage of that as a transmitter and get a passive radar. A lot of work going on that now and a lot of papers. Mm-hmm. So it does have future use. A lot of people working in that area and doing it in industry as well.
Yeah, I think the question was more about like the passive array, the phase array in like how phase array are affecting the passive radar. If there is any influence on phase array on passive radar, because you just mentioned that passive radar must be a cheap technology, and phase array, usually they're not cheap. I'm interpreting the question.
I see. But phase arrays are getting cheaper.
Okay, that's true. Yeah. Okay, I'll go to the next question. So there is a question from Isaac. It says that the linear MIMO configuration that you are showing that had 200 virtual element, so there is in a picture that you showed before, right? There was a linear MIMO configuration with 200 element, lambda over 2, has better resolution than the 10 element receiver array.
That's correct. Yes, that's true.
So it doesn't understand why you say that there is no MIMO resolution advance.
Oh, that's because if I didn't make it clear, you can have the using the same antennas they use for the MIMO. The same antennas they use for the MIMO. You can actually use them as a conventional array. And when you use them as a conventional array in the right way, it'll give you the same resolution and accuracy as the MIMO.
Yeah.
That's an important statement. And that's the reason I say the MIMO doesn't have that advantage that's claimed there. They just didn't do due diligence on what conventional can do. And when you really look at what conventional can do, it can do just as well as the MIMO for that application. The thin full array, where they get the factor of n better resolution. With 10 elements, they get factor of 10 better. They get equivalent of 100 elements. With 1,000 elements, they get equivalent of 1,000,000 elements. You can do that with conventional array just as well as with MIMO. And I do have a nice paper on that subject I'd recommend reading in the IEEE International Conference 2015 held in Washington, D.C. area. I have a discussion of that. I also have a paper in the Microwave Journal, earlier paper, but the one in the IEEE has a better way of doing it for the conventional. It's a better conventional implementation of what the MIMO can do.
Very good. So I believe there is no more question. We answer all of them.
They were very good questions. I thought the questions were very good.
Yes, you're right.
Yeah, very, so I commend the questioners on their questions.
Yes. So if there is no more question, I believe we can conclude this distinguished lecture. We thank Eli, Dr. Brookner. Thank you very much for presenting all these slides. They are very inspiring and motivating for us. For those of you still attending, I just want to remind that there will be another distinguished lecture next week. So please check our website for the information and register if you can attend.